Welcome everyone. Today we will discuss a fundamental concept in time series analysis, moving average models. Especially we were focusing on two simple models, MA1 and MA2. These models are widely used to model short-term dependencies in time series data. Before we dive into these specific models, I will give a very brief overall what moving average model is and how it functions in time series analysis. Let's begin by defining a moving average model. In simple terms, a moving average model, MA, is a linear model for time series data. It works by making the current value of the time series dependent on the previous error terms or shocks, which we call residuals. Here we can see the general form of the MAQ model, where the current observation xt is explained by a constant term mean, mu, the current error, epsilon t, and the previous error weighted by coefficients theta 1 up to theta q. We're focusing on MA1 and MA2 model, which are simpler versions of this general form. Let's look at the MA1 model, which is defined by this equation, xt equal to mu plus epsilon t plus theta 1 times epsilon t minus 1. In this model, the current observations depends on two components, the current error term epsilon t, which is assumed to be white noise with mean 0 and variance sigma square, and also the previous error epsilon t minus 1 scaled by the parameter theta 1. This simple model is often used to represent short-term dependencies in time series, as the current values relies only on the most recent past shocks. Next, let's calculate the mean of the MA1 process. To find the mean, we take the expectations of the both sides of the MA1 equations, as you see on the screen. Since the expectations of the white noise epsilon t is 0, the mean simplified to mu. Therefore, the mean of MA1 process is simply mu and means the constant term. Now, let's compute the variance of MA1 model. The variance of xt is given by variance of the sum epsilon t plus theta 1 times epsilon t minus 1. Since the errors are white noise and independent of each other, we can calculate the variance as sigma square times open bracket 1 plus theta 1 square close bracket. This shows that the variance depends not only on the error variance sigma square, but also on the coefficients theta 1. Next, let's talk about the optocorrelation function ACF of the MA1 model, which measures the correlation between observations at different time legs. For leg 0, the optocovariance is simply the variance we just compute, gamma 0 equal to sigma square times open bracket 1 plus theta 1 square close bracket. For that one, after some algebraic simplification, we find that the optocovariance gamma 1 equal to theta 1 times sigma square. For all x greater than 1, the optocovariance is 0, as the model only depends on the most recent error. Therefore, the AFC at that one is rho 1 equal to theta 1 over 1 plus theta 1 square, and for higher legs it is 0. Now let's move on to MA2 model, which is slightly more complex. Here the current observation depends on two previous error terms, epsilon t minus 1 and epsilon t minus 2, which coefficients is theta 1 and theta 2. The equation is xt equal to mu plus epsilon t plus theta 1 times epsilon t minus 1 plus theta 2 times epsilon t minus 2. This model is useful when the time series exhibits optocorrelation for more than one leg. To calculate the mean of MA2's process, we take the expectations of both sides of the equations, expected value xt equal to expected value of mu plus epsilon t plus theta 1 times epsilon t minus 1 plus theta 2 times epsilon t minus 2. Again, because the errors have zero mean, the expected value is simplified to mu. Therefore, the mean of MA2 process is mu, just like the MA1 model. For the variance of MA2 model, we consider some epsilon t plus theta 1 times epsilon t minus 1 plus theta 2 times epsilon t minus 2. Since the errors are independent, the variance is sigma square times open bracket 1 plus theta 1 square plus theta 2 square close bracket. As you can see, the variance can depend on both theta 1 and theta 2. Now let's compute the ACF for the MA2 model. At leg 0, the optocovariance is simply the variance gamma 0 equal to sigma square times open bracket 1 plus theta 1 square plus theta 2 square close bracket. At leg 1, we compute the covariance as gamma 1 equal to theta 1 sigma square plus theta 1 times theta 2 times sigma square, take into account that the interactions between epsilon t minus 1 and epsilon t minus 2. At leg 2, the optocovariance is gamma 2 equal to theta square times sigma square, and the legs greater than 2 is all equal to 0. Therefore, the AFC for the gamma 2 model extends up to leg 2. To conclude, we have explored the MA1 and MA2 models, which describe the time series with the shorthand dependencies on past errors. The mean of these processes remain constant, but the variance and optocorrelation functions depends on the coefficients theta 1 and theta 2. These models are particularly useful when modeling time series data that exhibit short-term optocorrelations. Thank you for your attention. I see you on the next one.